So I'm Daira Hopwood. These are my details. I do protocol design for electric coin company, and we work on Zcash. So this is basically how to scale a Zcash-like private payment protocol so that you can add nodes to the network and get better scalability. So the design space of sort of private scaling protocols is huge, and I'm just going to concentrate on my own proposal, which is hard enough by itself to get into 30 minutes, plus time for questions, hopefully. And so when I first did a version of this talk at ZCon, the Twitter trolls jumped on me and concluded that so Zcash was completely flawed because we were going to have to abandon everything and start again with this new protocol. This is a research proposal, so treat it as such. And Zcash sapling is pretty performant anyway. So this is what we mean by, or what I mean by horizontal scalability. You can add compute power in the form of more nodes or and get higher transaction throughput that scales with the number of nodes. And so there will still be bottlenecks. So eventually you will hit some other scaling limit. In particular, I'm only aiming for what Ethereum people call quadratic scalability. So there are coordination bottlenecks between the shards that are handling some of the blockchain. So that means you can basically asymptotically you're squaring the throughput rather than allowing arbitrary better throughput. But that's probably going to be sufficient in practice. And we don't want to compromise on privacy. So earlier we were talking about protocols, this idea of this dark room. And Monero is another example of protocols in this category, where you try to obfuscate the transaction graph by making each input possibly correspond to some small O1 number of outputs from previous transactions. And it turns out that doesn't actually give you the privacy that you want. Whereas in Zcash, any input could correspond in principle to any previous output that the attacker doesn't control. And we have some secondary goals. We don't just want to support scaling. We want to minimize the trust requirements on clients with low bandwidth and storage. We want to improve network layer privacy. So we have the privacy of the blockchain itself. What can an adversary infer from the visible part of the blockchain, but it's also what can a global passive eavesdropper infer. So we would like to improve that, which is complementary to the blockchain privacy. We'd like to reduce the cryptographic assumptions because we're currently using quite strong assumptions in Zcash. And we would, so transaction malleability, which is an issue for Bitcoin before SegWit, is also a problem for Zcash.
Does the malleability comes in only in the non-transparent, transparent to transparent, right?
It comes in both, actually, for complicated reasons. That I can't, yeah. But partly because of the interaction with the transparent protocol. Okay, we're not trying to support general computation. We're not trying to reinvent Ethereum yet, because it's basically hard enough to do privacy and scalability without doing programmability as well. But there's nothing really here that precludes going to a programmable protocol later. In fact, the recursive composition that we're going to use is very useful for programmability. So so one layer of recursive composition is used in Zcash to support programmability as well. And no one really knows how to do good auditable contract languages yet, I think. I quite like ZKVM, but yeah, anyway. And we're going to basically strip out the transparent support, I think, because it was basically just a crutch for adoption. So try to be partly compatible with Bitcoin, which was reasonably successful, but I think we underestimated the downsides of having a protocol that was only partially shielded. And in fact, what you want to do is maximize the anonymity set. Also, we wouldn't be able to be compatible with Bitcoin anyway, because Bitcoin script is too complicated to put in a circuit. Okay. So all of this stuff is out of scope just because it's too complicated to explain in half an hour. So if we just wanted to hide amounts, then we would use Peterson hashes and do something like confidential transactions, but that's not enough. We want to hide the transaction graph. And this plausible deniability, so that the idea that you don't know exactly which previous output corresponds to an input, but it's something in a small set, it doesn't really work in practice. And this talk by Ian Meyer at ZCon1 will explain in lots of detail why that's the case. Okay. So this is basically my proposal, or the things that I'm going to use in my proposal. So sharding, similar to what Ethereum is proposing, that you split the blockchain state into some number of shards, and then your throughput limit is basically limited by is per shard rather than per blockchain. It's going to be slightly different than what Ethereum is proposing, but I'll go into more detail about that later. We're going to use Recursive Snark validation, similarly to Coda. So what proportion of the room know basically how Coda works? Okay, so I'll explain in more detail what recursive validation is and how we use it later. We want to use transparent snarks, partly because of all of the recent progress in transparent snarks, partly because setup ceremonies are a pain. People don't trust them. There will always be some subset of users who won't trust a setup ceremony and will invent conspiracy theories that everyone was colluding, or that you'd backdoored the software, something like that. It's basically, the future is transparent snarks.
Do you know that there's always going to be this subset because you're going to always be in that subset? Partly,
yes. Partly because I basically don't trust computers to be free of side channel attacks. Anyway. We're going to use a mixnet for the network level privacy. Basically, so this is in Zcash, what we do is we broadcast all transactions to the whole network, and then you trial decrypt every transaction looking whether you are able to decrypt it using your keys, and that clearly doesn't scale. Okay, so this is basically how we're going to use recursive validation. So here in this example, we have 3 shards. So we've split the network into 3. And this time axis is basically, you can think of these as blocks. So we're going to use snarks to summarize the state changes that we make. And this triangle represents the fact that we're summarizing this to a ZK snark at this corner here. And we're doing that for each shard in each time period. And then this blue triangle So if we have another layer of the system that is processing the summaries from the shards and also the summary from the previous block, and then creating a new summary of the state of the system. So this is fairly straightforward. This may actually be an oversimplification for the real system, because what we're assuming here is that it's possible to do these summaries quite quickly in comparison to the block time. If that were not the case for the actual proving system that we're using, then we would just summarize a previous block, and that's basically what Coda does. But it's simpler to describe it this way. Okay. So let's have a look at the existing blockchain model as used in Zcash to see what's wrong with it from the point of view of scaling. So we've got transactions describe changes to the state. We collect those into blocks. A chain is a sequence of blocks. We've got consensus rules that determine sort of which of these chains are valid. And so there's an interesting observation that we can make here, which is that most of the transaction rules, there's not much interaction between how the rules apply to each transaction, except that we've got to prevent concurrent double spends. So the rules for a transaction depend only on the transaction contents and the previous block. So we've got some consensus protocol, which is basically used to define the ordering of transactions. And the assumptions that we require for security of that ordering are kind of out of scope for this. So we could use proof of work, we could use proof of stake. What I'm going to describe here is basically independent of that layer. And so people think of blockchains as a chain. They're not really, they're trees, and you have orphan blocks, and you eventually end up ignoring the orphans. But it's really always a tree. But you have some rule for deciding which is the best leaf. Okay. So applying this to the Zerocash protocol, which is implemented in Zcash, we're basically using the UTXO model. So are people familiar with the UTXO model already? Okay, yeah. And instead of UTXOs, we call them notes. And they have a value, a commitment to that value, and something called a nullifier, which we're going to use to detect double spends. So these are binding and hiding commitments. I'm going to assume that this audience knows what a commitment scheme is. And then when you create an output note from a transaction, you reveal its commitment. So you have some global data structure, some accumulator that is storing all of the commitments for all of the output notes that were ever created. And when you create a note, you also fix its nullifier, but that's not revealed when you create the note. And in fact, the party that creates a note doesn't know it either, because it's dependent on the recipient's private key. So it's deterministic, but you're creating the note and you don't know its nullifier. And that's going to be what prevents even you as the creator of a note from determining when it's spent. And obviously, if even the creator of the note can't determine that, then no one else can either, except the recipient. So when you spend a note, you reveal the nullifier, and because that's deterministic, there could be only one nullifier for a note, then that's, if you prevent nullifiers from reoccurring on a blockchain, then you're preventing double spending. And then you've got to prove in zero knowledge that it's a valid note in other words, that its commitment is in the accumulator, and you prove that in zero knowledge, so that no one, so apart from the recipient, can, apart from the spender, can see which note was spent. And then you also have to prove that the nullifier and the commitment are linked correctly, so they belong to the same note. And you need to prove that you were authorized to spend the note, so you hold it. This combination of the commitment tree state and the nullifier, of the commitment tree and the nullifier set, that's called a tree state. So there's a tree state after every transaction, and then there's a tree state for each block. And when you create the proof for a spend, for example, you will refer to some previous tree state, usually a fairly recent tree state, and then the note that you're spending could be anything that was, any of the notes that were present before that tree state. So, some information about zero-knowledge proving systems. I guess people know all this already, but I'm going to sort of emphasize certain properties of zero-knowledge proving systems that are important for this protocol. So, we have a statement. It has instance variables and witness variables, and we're defining some relation on those that needs to be true. So, we can find short proof that we know the witness that makes the statement true, and we don't reveal any other information. So this has to be a proof of knowledge because we actually need to know that for example, if you're spending a note, then you have to know the private key. It's not sufficient to prove that a private key exists because it might not be yours. And the proof is just a string, which makes this suitable for use on blockchains, because you can just include it in the transaction. Okay, so in more detail how Zcash works, I've already sort of gone through how the receiver of a note knows that the note is addressed to them. They just trial decrypt all of the outputs. And then, so this requires the blockchain to be a broadcast channel. And that's going to be a scalability problem that we need to fix. And our privacy is actually, from the proof system point of view, it's usually unconditional in a system like Grot16. You're also depending on the public key encryption for privacy. But you're not depending on any strong security assumptions to get privacy from the proof system. So this detail about Sapling is the sort of more recent version of the protocol where we upgraded it and we changed the proof system to Grot16. We did a lot of optimizations to the statements. And we got the cost of a spend proof down from, say, 50 seconds to just a few seconds, say 4 seconds. So that is really important performance improvement in practice. And we took the opportunity to sort of streamline some of the crypto. So actually, Sapling works a little bit more like confidential transactions, in that it's creating paydosen commitments to each note, to each value, and you're making sure that you're using the homomorphic property of the paydosen commitments to make sure that everything balances. We don't need anything else there. So another useful feature of Sapling is this separated signing. So you can have a hardware wallet that only needs to be able to do signatures in a variant of Schnorr. This is actually a randomized variant of Schnorr, which you need in order to not to leak information that would otherwise be hidden. And then the prover can be separated from the hardware wallet. So the hardware wallet is doing the authorization that you were able to spend, and then so that's linked to the zero knowledge proof. And then you send it to the transaction, it gets mined. And this hardware wallet, you can do that in, you can do a red DSA signature in a few hundred bytes of memory. So this is suitable for hardware wallets like Trezor and Ledger. It's taken us longer to actually implement that than we originally expected, but the protocol supports it. So the bottlenecks. All of the validators of the blockchain have to validate each transaction, update commitment trees, update nullifier sets. The transactions have to be broadcast, both to validators and to parties that are receiving notes or tokens in general. All of the potential token receivers have to trial decrypt each output. So miners have to validate, or they should validate transactions before they put them in blocks. They don't always do that. You have to broadcast the blocks. A block includes all of its transactions so that they're actually literally included in the data of the block. If you've been offline for a long time, then you have to do all of the work of sort of updating your copy of the commitment tree for all of the transactions that have happened. Yeah, and if you hold notes, then in order to be able to spend them later, you can't just do that immediately. You have a witness that for each note that you have to update depending on the blockchain state in order to be able to do the proof in the Merkle tree that you own the note. Okay, so this clearly isn't scalable because of all of those bottlenecks. So naively, what you could try and do is have miners include proof that all of the transactions in the block were valid. So what would the problems be there? So you can't do that in a single proof because it's a variable amount of computation. And in most proof systems, you can only prove a fixed arithmetic circuit of a given size. At this point, we're not considering things like recursive validation. It doesn't address the bandwidth issues at all, because you still have sort of the same amount of data that you had before. Detecting transactions involving you still has the same overhead. And you still have to store all of the commitment trees and the nullifier sets. Just broadcasting all of the transactions to every participant in the network by itself isn't scalable. So we can use sharding, which is this idea of splitting a blockchain into multiple shards. And so there are several ways of doing this. You can try to make it more or less transparent to the participants in the network. So this is basically a measure of how much participants need to take into account the fact that the network is sharded, what additional protocol complexities they have, and is that complexity visible to users? And I think we should be able to make it not so visible to users, but wallet implementers will still have to take on board some of that complexity. And that's relatively fine. Okay, so these shards don't have to be complete copies of the system. Every time I try to explain sharding, people have sort of a lot of baggage and assumptions that maybe they've taken from database uses of sharding, or where Ethereum, or wherever they've encountered sharding before. So try and sort of scrub that from your mind and so just think of the basic idea of sharding. So the kind of sharding that I'll be talking about in this particular design, addresses are global, so addresses are not specific to a shard. We're not splitting the anonymity set, so just because a transaction is on a particular shard doesn't mean that its anonymity set has been limited to that shard. End users don't really need to be aware of sharding, even though it might have an effect on the latency of their transactions. But we do shard the processing of transactions, which we have to do to achieve the goals of scalability. We shard the storage, so it's not the case that everyone still has to have a full copy of the blockchain. We shard the processing of nullifiers, so we're going to design it so that by construction, only the transactions in a particular shard can be potential double spends. So transactions that are in different shards can't, by construction, be double spends. And you're not going to have to catch up with other transactions. So we're going to use recursive validation for that. And I've already mentioned this fact that there's still going to be a limit because of coordination between the shards. I can mostly skip this because what it's saying is that this layer of the protocol is not dependent on how we decide what transactions are going to get into the train. That's an orthogonal issue. Okay, so some other properties of zero-knowledge proving systems, besides privacy, that are useful here is the proofs are short and they're efficient to verify. So the fact that they're just strings is also relevant to scaling. Okay. So the basic tool that we're going to use here is recursive snarks, and this is the idea that within the statement of a snark, you can verify another snark proof. And so if you do that in the form of a tree, and you can verify lots of proofs at the leaf layer of the tree, and end up with just a single proof potentially, you can verify that indirectly convinces you that all of the proof creators knew the witnesses, and all of the leaf proofs are true statements. Notice that lots of different parties can contribute to the proofs that go into this tree, and they may all know different things. So we're not saying that this tree construction is equivalent to having a single snark, because a single snark would require a single prover to know everything. But this is actually a feature in our context. So we can basically do a generic kind of transformation of a protocol that makes flat use of zero-knowledge proofs, so no use of recursive validation, and we can transform that into a protocol that uses this technique. But we're going to have to add proofs that weren't necessarily necessary in the input protocol. So a lot of the things that we would previously have proven outside the circuit are going to have to move inside the circuit in order to be able to prove everything we want to at the top level. So that's going to add some overhead, but it turns out to be acceptable overhead. Notice that we don't necessarily need zero knowledge for the scaling. So we might need zero knowledge at the leaf proofs because we're we're trying to allow people to use private keys and other information that only they know. But this construction of the tree of proofs doesn't necessarily need zero knowledge at the higher layers. It just needs the proof properties, the soundness properties. So for language geeks, there's this idea of S-attributed grammars that we can use to describe recursive proof systems, but I won't go into detail about that. So some information on some recent developments in Snarks. So we now know how to create universal proving systems where you don't need to do a setup for each statement. But there are still some disadvantages to using pairing-based Snarks. So we'd like to reduce the assumptions a little bit. We could use something like bulletproofs, but it has linear verification in the circuit size. And in practice, that's too large for blockchain applications for the kind of statements that we need in Zcash, at least. There are plenty of statements that are small enough that you can use bulletproofs in blockchain applications, but this is probably not one of them. So here's an explanation of some recent schemes. So we have sharks, which so they have a prudent mode and an optimistic mode. The optimistic mode is faster and relies on pairings. And the prudent mode is a little bit more like sort of bulletproof style. And we can regenerate proofs if the optimistic mode assumptions are broken. So that's useful. I think to some extent that's been overtaken by events because we now have so fully transparent proofs in the form of Supersonic, but in any case, it's still useful. Halo, which is joint work between me, Sean Bowe, and Jack Grigg. It's a public coin proof system, and it provides something called amortized succinctness. So that's basically the idea that you take a proof system that has linear verification time, but you can chain proofs or put proofs in a tree, and then your top-level proof still only requires linear verification time. You don't have to verify all of the constituent proofs. And again, this relies on relatively weak assumptions. And Supersonic, so very recently, it's the first Snark to be transparent, and it's also fully succinct, so both in terms of proof size and in terms of verification, asymptotic verification. So this uses this idea of this kind of cryptography based on class groups of imaginary quadratic orders, which are proposed quite a while ago, but are sort of fairly unfamiliar to implementers, and there's going to be a lot of engineering work, I think, to improve their performance.
Question there?
Yes.
It's the first Snark to be transparent if we exclude Stark with the T that stands for transparent?
Yes, you are correct. Yes, Starks are transparent and also succinct for individual proofs. I apologize to the Stark authors because that's actually wrong. But Starks have quite large proofs in practice, hundreds of kilobytes. Whereas Supersonic has sort of proofs of less than 10 kilobytes for, say, 1 million gates. So a lot of this innovation in sort of proof systems has been enabled by this idea of splitting the Snark protocol into an information theoretic part and a polynomial commitment scheme. And that means you can mix and match the two halves of the Snark. So you can use different information theoretic protocols and different commitment schemes This is a particular kind of commitment scheme on polynomials that allows you to verify evaluations. So because of this, this refactoring of the design space, we can expect some really rapid progress from now on, I think. And so I'm going to assume that we can solve all the other engineering problems and get really efficient public coin snarks that are succinct and practical efficiency for recursion. And I'm also going to assume that this proving is efficient compared to the block time. And we could relax that assumption if we wanted to. So that's just for simplicity. Okay. We don't need this. So these are the additional things that we need to be able to prove sort of now within the statements that we previously were verifying outside the statement. So things like the red DSA signatures that I was talking about, and the overall balance, non-malleability, and importantly the nullifier set updates, which are concretely quite difficult to do because they're Merkle tree non-membership proofs. So a membership proof is relatively easy, a non-membership proof is much more complicated. Okay, so we're already using Merkle tree accumulators for the note commitments because that turns out to be the most efficient form of accumulator to use. Possibly that's been altered in the past few days because of this new idea of using, there's a very recent paper that may affect that, but we need to add an accumulator for the nullifiers and be able to prove that a nullifier has not already been used. And I've got some detail here that I probably don't have time to go through about how the nullifier accumulator works. The basic idea is that you're going to partition notes according to you're going to split the nullifier space across shards. So a nullifier that has a certain prefix will be in a certain shard. And what this allows is, so because only nullifiers with a given prefix are in a given shard, you can do the double spend detection independently for each shard. And that really simplifies things. And this is more about how the nullifier accumulator could work, but basically it just has to do non-membership proofs. And you can combine a list of nullifiers and create a proof, create an update of the accumulator for the nullifiers, and also a proof that you added all of those nullifiers. Okay. So these are the protocol bottlenecks that we've solved by doing this kind of thing. So all of these things that say per shard, we now only need to do them independently for each shard. But we still need to broadcast all of the transactions, and the token receivers still need to check each output. So in order to solve those problems, we need to basically, instead of broadcasting transactions, we need to use a mixnet to send them. Because we also need to maintain the privacy. We don't want a privacy regression because of the fact that we're not broadcasting transactions. So Zcash as it stands is basically an anonymity network combined with a payment protocol. So if we're going to shard it, then we need to find some other way to do the anonymity network. And the most practical alternative there is mixnets if we want to preserve the same security. Okay, here are some proposals for mix sets. The details don't matter. There's already a prototype of support for Zcash on cats and posts, which is a recent mixnet design, so based on the Lupix academic proposal. And here's, so this is the last slide actually. So there's some unresolved problems. So in order to solve non-malleability, you really want to know that your transaction got into the chain, and there's some details about how you prove that. You probably can use receipts, but then what if the transaction is included or you don't get a receipt? So there's some details here that haven't been resolved, but basically it works. Okay, that's it. Questions? Do we have time for questions?
So we have time for one question.
Okay.
So is there any quick question in the audience?
So you say it works?
Okay, it works in my head.
That's a quick question.
It works in my head,
Okay.
is the answer.
Thank the speaker one more time. Thanks.